So let me recall a little bit before we move to the next slide. What do we want to do here? We want to build a binary tree inside an array data structure. The binary tree is a special binary tree. So not arbitrary binary tree. Okay? Arbitrary binary tree, so we can draw, different shapes, and many times it could be very unbalanced. That's something that cause poor performance. Unbalanced binary tree would result in poor search performance. We don't want that. We want our binary tree as close to balanced binary tree as possible. So this one, we call it near complete binary tree, because the complete binary tree is the most balanced binary tree. Most balanced binary tree. So this one, because we cannot get a complete binary tree. Only when you have the number of nodes 2 to the k minus 1, right? But remember, 0. Array element as 0 cannot be used as the heap number. So in order to have a heap that corresponds to a complete binary tree, we need a 2 to the k. We need a this many power of 2. This many nodes, we can get a complete binary tree in a heap. Okay. Skipping the first one. Otherwise, for a usual binary tree, for example, if you apply the binary search, you can draw a binary tree, right? So for the binary search, you can draw a binary tree. When do you get a complete binary tree? N equals 2 to the k minus 1. That's the binary search case. But here, for the heap case, this is the heap case. Heap case, right. Heap case. Because the first node cannot be used as the heap node. So that, all right, yeah.
Wait, you said first node.
A of 0. Remember this one? A of 0 is never used.
Okay.
The reason, parent-child relationship cannot be separated, right?
Mm-hmm.
Yeah. I and the 2i, the same one. So we do not allow that to happen. Yeah. All right, so that's the, and another thing, max heap property. In order to support our Heapsort algorithm, here we require this max heap property. Okay? Max heap. And with max heap property, we can define a max heap data structure. Everywhere, this property is there, satisfied, everywhere. That's the max heap. If at one place it is not satisfied, we cannot call it a max heap. Now, new slide. This time, I want to show you a max heap example. So given an array, usually we do not have a max heap. You need to do some work. You need to build a heap. You need to run some algorithm to build a heap. We will do that next. After this example, we will build a max heap. Look at this heap. look at this one. If it is a max heap, check. If the max heap property is satisfied everywhere, every location, everywhere, you get a max heap. That parent-child, the value. So the parent value is always greater or equal to both left or right values of left or right child. Here, underlying array that stores this max heap, like this. Here, I want to let you visually connect. How can we connect an ordinary array with a heap, binary tree structure? First one, we skip it. We cannot use the first element for the heap. Then, 16, we put at the location 1. Then, two child nodes, 2, 3, with value 14 and 10. Okay? Then, for the two child nodes of node at position 2, 8, 7. Okay? Connection. Hidden connection, you just imagine the connection. Okay? Right. Then, another two channels for node at position 3, index 3, like this. Okay? And so on. In this way, you can see we can store a near complete binary tree in an array, ordinary array, without using linkers, without using pointers. You do not need explicit, concrete pointers. Just a math formula relationship. Okay? We use math formula to connect them. Yeah. Soft connection. Okay? Not hard connection. Soft link. Yeah. Very effective. Yeah. We won't mess up. Yeah. And you can also see covering all the locations except the location at index 0. So we do not skip too many array elements. We use all of them other than first one. Right. Maintaining the heap property. The heap property, sometimes when you do some manipulation operations, you may violate the heap property. Remember, we need to work on the dynamic data. When a new data item comes in and you drop it in your current max heap, most likely, so at some place, the heap property is violated. Max heap property couldn't be violated. So you need to recover it, maintaining heap property. All right. So when the heap property is violated due to some operations, insertion, deletion, etc., how to fix it? So we need to get this one. Idea is very simple, so let's just work on this local triangle here. P, L, R, these three nodes form a local triangle. We want to fix the max heap property violation. If there is some violation occurs within this triangle, how do we fix it? Very simple. Put up here and use the pseudocode to show you how to fix it. Violation occurs locally, but we need to check everywhere, right? But if we can fix locally, we can fix globally. Alright, some violation. So we assume there is a max heap attached at the left subtree with L as the root node, left subtree. Also, another max heap attached at the right subtree with R as the root node. So let's only work on this triangle, local triangle. Local fixing operation. Local fixing operation. Right. Check for violation global. After we fix it, you need to check it if you have violation other places. Okay? Only when you make sure no violation everywhere in the whole tree, then you get max heap again. You recover max heap again. All right. Let's work on the detail. So here we call it local heapify operation. Local heapify operation. The details here. Recursion approach here. Recursion approach. Recursion. Here I'd like to remind you. When we do recursion, think about it. Last time when I talked about in-place algorithm, in-place. In-place algorithm, we need an extra storage space used, bounded by, in this category, big theta of 1. But if you use recursion, your stack could grow, right? When your stack grow inside the main memory, then the extra space used could be larger than you can get out of this. So it may not be an in-place algorithm. To solve the problem, you may like to convert it to iterative algorithm, not recursion. If it's possible, you want to convert it to iterative algorithm. Then you won't have the stack. Iterative, you just move step by step. Okay? You do not push into the stack. All right? So the memory you use every time, for example, when we process local triangle, we just use the memory that is sufficient for the local triangle temporarily, right? After that, yeah, the temporary memory can be reused for the next local triangle, right? Next local triangle, all the way down to the bottom, to the end. In that way, we try to reduce the memory consumption. Memory consumption, right? This kind of things, when you design your algorithms, you need to think about it. Okay? At least you need to think about it. Remember the design goal for the heap sort. One of the 3 requirements, we want to make it in place, completely in place. That's one of the objectives. All right, so that's why I make some comments here. Okay? Here, when we understand the first round, let's take this recursion approach. Okay? Let's take this recursion approach to understand. Later, we want to change recursion approach to iterative approach. For a heap binary tree, it's not hard, but because the binary tree, you know the structure. When you move down, you can figure out locations easily, right? Yeah. Hopefully, you can figure out how to, do the heapify operation globally, not locally. Locally, we don't worry. Globally, with the integrated approach. Yeah. All right, put a question mark. All right. Yeah, so let's work on these three nodes. All right. Pseudocode. First, let us compare A of I. If this inequality is true or not, less than A of 2i, left child. If true, violation, right? Yeah. Because max heapify, we need A of I greater or equal to A of 2i, based on the max heapify problem. But if this inequality holds, that means we have a violation. Max heapify. Property violation. So we do the swap operation. Although you can, but this one, the pseudocode, we delay the swap operation. I will explain. So why we delay the swap operation. Okay. So here, if this happens, we store some information. We store. We use a flag. We use a variable. Largest variable. This is a variable. Largest equals index of left child, 2i. Largest, you know the meaning, the value, largest value, currently, it's in this location, 2i location. Not I location, 2i location. Currently. So here, the purpose, we want to delay the swap operation. Some people, they may like, when they detect A of I less than A of 2i, they do the swap immediately. Although you can do it, it's not wrong. But here, we like to delay it. Right, next thing. Else. Yep. Else, because else, that means A of I greater or equal to 2i, right? A of I greater or equal to 2i. That means no violation between these nodes, at least. No violation between A of I and A of 2i. No violation, so largest equals I. Yeah. Largest value occurs currently in I location. Right? That's just the one half. We have to compare with the right child. So we do the second half. This, for the second half, we will use A of largest value, either I or 2i. Just one of the two, A of largest, less than A of 2i plus 1 or not. If this inequality is true, we update largest variable, we store 2i plus 1 in this variable. Otherwise, do nothing, right? Yeah, because largest, it stores the location with the largest value already, right? We don't do anything. So the last step, after these two if statements, then we need to consider doing that swap operation or not. Last step, before you do the swap, you need to check if the largest not equal to I or not. If it equals to I, you should not do swap, right? Equals I, no violation, then you are done. Okay, do nothing, right? But if the largest is not equal to I, you need to do the swap. Swap A of largest and A of I. after the swap, you fix the max heap property violation locally within this triangle. That's it. That's the whole heapify, local heapify operation. Very easy, right? Very easy. Here you can see, although we can write a code many different ways, but this one, we try to do it in the best way. Why here I mean the best way? Because we try to reduce the number of swap operations. Let's compare it with another way. The first time, if you detect A of I less than equal to I, you can do the swap operation, right? All right, after that, the second time you compare, parent value, right child value. If there is another, you can do another swap operation. So you may do two swap operations, right? Here, we do at the most one swap. Okay? At the most, less than or equal to 1. At the most, one swap operation. We never do two operations. Why it matters? You may ask me, why we, if it is possible, we try to reduce the swap operation as much as we can. Why it matters? Here, let me expand the background a little. Background. Although here we use an array to build a max, think about it. How large is the array size? Can you imagine how large is the array size? Yeah. It varies, right? Nobody can predict how large is the array size. For each array element, how large is the memory size used for each memory element? Nobody knows, right? It could vary, right? Yeah. But here, because you have the background of object-oriented programming, right? OOP, you have that background. Object-oriented programming. Here, let me use that background. Yeah. All right. Can we create an array? Can we create an array for an object? Here, not numbers, integers. That's very easy. Is it possible we create an array for? So here, an array of objects. You have no problem understanding, right? How large or what memory size is assigned to each object? Do you have an idea? How much memory size is assigned to each object? It varies, right? Sometimes could be big, sometimes could be small. Depends on what is the object, right? Your object. If you have a simple object, you use very little memory. But if you have a gigantic object, you could use a lot of memory. Right? The object, nobody knows how large is the size. All right. Think about it. You may have the situation your object could be quite large, right? When your object is very large, when you do swap operation, is it very expensive? Swap means you copy, okay? You copy the data. Yeah. So if you want to swap data between two objects, you need to use a temporary object, right? You copy to the temporary object. Then, so 1, 2, 3, right? 3 copy operations, assignment, data assignment, copy operations. Yeah, so that could be pretty expensive. pretty expensive. So when you have a chance, you want to save it here, right? Save one swap operation, you save, you know, quite a lot. Think about it. So here, after this class, every time when it is possible, we want to improve our act. Okay? Here, this is the place we want to improve our act. Yeah. All right, so that's the comments. Why are we doing it this way? Yeah, because what I explained for this simple pseudocode, I spent a lot of many minutes explain, because some students, you may feel you can make it simpler. Yeah. First time, one swapper, the second time, another swapper. The code, it looks shorter, right? It looks shorter, but actually the cost is high. The code is shorter. Yeah. The code is shorter, but the real concrete work, you do more concrete work. So we're willing to write a little more code to do less work, right? Think about it. We're willing to write a few more lines, but the computer works less. How about that? Okay? Yeah. How about that? Try to, understand this point. Okay? Yeah. All right. Let's move to the next topic. 8.4, heap example. So this time, maps heapify example. I show you using concrete example to show how do we do maps heapify operation. This time globally, not locally. Okay? Globally, we need a sequence of local heapify operation to complete the global fix. Right? Yeah. This example, that shaded node mark violation location. The violation location, next heap of property violation location. We want to fix it. Then mark this local triangle, apply our local heapify operation. After that, so we do one swap operation between these two nodes. That gray node moves down, but when it moves down, it can carry the violation one level lower, right? Look at this local triangle. You can see another violation. So when that bad node moves down, it can carry violation down one level down. Then we need to do another local fix, local heapify operation. After that, because this node 4 already reached the bottom, so we don't worry about more violation, right? Already at the bottom, there was no local triangle around this node, this bad node. Yeah. So when it hits the bottom, we're done. Okay? Yeah. So that means when we do local fix, we need to keep track of this node all the way down to the bottom. All the way down to the bottom. The question. Can you implement this code without using recursion? We want to avoid recursion. So the question, we want to use, let's say, while. We want to use a while. You can also use for loop if you like. Okay? For loop or while. So you can do this kind of operation, because in that way, for loop or while loop, we do not use recursion. We do not use stack. So we can save memory space. We can make it in place address. Think about that. Okay? All right. Yeah. Now, example, building a heap. Now, given an arbitrary array, the data pretty much random, we want to build a max heap. Let's look at how much work we need to do to build max heap. This array with random numbers, like this. So we want to apply max heapify operations. Good heap means max heapify operation. All right, so let me show you. To do max heapify here, the order is important because you have so many different ways to apply max heapify operation. So the order to apply max heapify operation, that's important. Here, let me show you the order. Actually, order here we use the bottom up approach. Bottom up. Bottom up approach. We start from bottom. Okay? At the end, the last local triangle actually start from this one. The last possible, there is no right end, right? But we still use a local triangle to cover it. This is our last local triangle. All right? No violation, then we move to the next one. This is our next one. Then we detect there is a violation, so we apply max heapify operation to fix it. After the fix, swap operation between these two nodes, we fix it. Then, next time, look at moving up. Yeah, because the bottom level we're done, we complete the bottom level. One level up, from right to left. Okay? Follow that order to fix all the possible violations. Here we detect the violation, we should do swap operation between these two nodes. After that, then we move to this local triangle and we detect another violation and we should do another swap operation between these two nodes and the last local triangle here, the last swap operation to fix it. Yeah. But the last one, if it, remember, we need to move all the way down, right? Yeah, all the way down. Yeah, here. Not just last one, anyone we need to move all the way down. Yeah, the previous one, yeah, let's say, one here, yeah, because after the swap, you need to move one to the bottom. Yeah. All the way down to the bottom. Okay? Yeah. If there is a violation, we need to keep doing it until all the way down to the bottom. Okay? After this step, after we finish, top level, then we complete the whole process.
When you recheck to you go bottom up once, do you just keep going through bottom up until there's no violations?
Yes. But each one you need to make sure, follow the path to the bottom. Keep checking. Violation. Remember? Yeah.
Recheck from the top to the bottom?
All right, so suppose here there is a violation. After you do swap operation, 4 is here, but you need to check other violation until you reach the bottom. Do not just after you do one fix, you stop. that you may not complete the fixing operation. Yeah. So here, this example, actually, you do max simplify operation twice. The first time, this swap. Not done yet. All right. Second time, another swap operation. And the same thing everywhere. Okay, everywhere. When you start somewhere, keep doing things like this. Yeah. All right. So here. Then you can see we get a maximum. No violation anyway. Right? No violation anyway. So our result, we get a max here. The question, how much work we need to do for this maximum? How much work? Yeah. If we need to do too much work, then we may not want to take this action. So we want to do analysis. We want to see how many comparisons do we need to do. Yeah. So when you check violation, you do comparisons. Oh, sorry. Yeah. So the part A, we finished part A. So now let's move to part B. All right. In order to estimate how much work we need to do, we need to do a lot of preparation. The first preparation, 3.1, heap nodes in each level. Heap nodes in each level. Yeah, here, people may. So here, when we talk about this level concept, many students may get confused. Heap level and binary tree level, they are different. Here. So that's the reason. Because many students use the binary tree level. Okay? Here, heap level. Because our heap is very special. Heap level is not equal to the binary tree level. Okay? All right. So let me show you why it's different. Number of leaves in the heap. Let's look at first the question. Special question. You know leaves, right? Given a tree, you know leaves concept, right? Leaf concept. Leaf node. What is a leaf? A leaf node does not have any child, right? That's what we call a leaf. A leaf node does not have any child. That's simple. Okay? A leaf node, that's for the general case, not necessarily binary tree, any tree. Okay? A leaf node does not have any child. All right, now we get back to heap. Given a heap with n nodes, n. Right. And so here I need to tell you that. Yeah, because there is 1.5 here, let me make it with n nodes, right? So other than 0, 1, 2, 3, n. Okay, not n minus 1, because after we exclude location at 0, we want to have n nodes. So here we assume we have a heap with n nodes, like this. Now my question is, how many of these nodes are the leaf nodes? How many of them are the leaf nodes? We want to count that. Describing leaves. All right, in this max heap, what are those nodes? They are leaves in this violation. No child nodes. All right? Here. Can you see these nodes? These 5 nodes. They are leaf nodes. All right. Now, we want to get a formula in terms of n. Because here, any positive integer n. We want to derive a formula to give us the number of leaves. How to do it? We explore the parent-child relationship, this one. Here we use the left child. Why we do not use the right child here? We use left child. We do not use the right child. Why we do not use the right child? Look at this. Because the right child may not be available. Hey, how do you know the right child is always available? Nobody knows the right child is always available, right? But left child, if a node is not a leaf, left child is always available, right? If a node is not a leaf, the left child is always available. So that's why we should use the left child, not the right child. Okay? All right. Now, can we use this parent-left child relationship to help us derive the formula that gives us the number of leaves in a heap? That's what we want to do. Okay? How do you describe a leaf? A leaf node. Can you use inequalities to describe a leaf node? Index I, yeah, let's assume a node has index I. Can you find some inequalities? If this is a leaf node, what inequalities it should satisfy? Okay? All right, so let's assume I corresponds to a leaf node. Let's assume that I location, this node, corresponds to a leaf node. Okay? Assumption, if this is a leaf node, then when we double its index 2i, what would you get? We double its index 2i. What will you get if it's a leaf? It's a leaf. Well, you double. What do you get? 2i, what inequality do you get? Inequality. 2i compared with n, greater or less? Greater or less, 2i compared with n?
Less. Or
If less, yeah, let me tell you. If less, that means 2i corresponds to left child of I, right? It has a left child. Can it be a leaf? A leaf cannot have any child. If your 2i less than or equal to n, then this node has a left child. It's a contradiction, right? So the only thing you can get 2i must be strictly greater than n. Okay? Yeah. 2i, so here we call out of bound. 2i out of bound. Can you see 2i must be out of bound? Yeah. If 2i is inbound, you have a left child. Okay? So 2i must be out of bound. Okay? What do you mean out of bound? Greater than n. Strictly greater than n. That means out of bound. Okay? Alright. Meaning no child. Yeah. So n, 2i must be strictly greater than n, but I must be within the bound, right? I must be a node, I within the bound, but 2i out of bound. How about this description? This is an accurate description for a leaf. For a leaf node. Okay? Alright. Now, can you tell me how many i's that satisfy this inequality? How many i's satisfy this inequality? Then you will know how many leaves you can find in the scheme. How many leaves you can find in the scheme? Okay? Yeah. Let's do transformation on this inequality. Yeah, here it's hard to see it, right? Directly. When you hard to see something directly, you may like to do transformation to see it better. Let's do transformation. All right. Index range. And we divide 2 both sides. We get n over 2 strictly less than I. Strictly less than I. Then n over 2 may not be an integer operation, right? N over 2 may not be an integer operation. We want to get inequality with integer operation. You can use ceiling function, floor function. But we don't like a formula inequality here without integer expression. N over 2. Sometimes it is not an integer expression. So that's not convenient to use. So we want to change it to integer. How can we write an equivalent inequality but with integer expressions? What is the smallest index that's strictly less than n over 2? Strictly greater than n over 2. The floor function of n over 2 plus. Look at that. Now ceiling function. If you use ceiling function, it may not be strictly greater than. Yeah. Think about it. Some students may like to use the ceiling function of n over 2. If that, because sometimes it could be equal to that, right? It could be equal to that sometimes. We don't, because here, strictly greater. So that's what we, not what we need. But if we use this expression, it's always strictly greater than n over 2. Always strictly greater than n over 2. How about that? Okay? And it's an integer, this is an integer expression that satisfies our requirement. Okay? Alright. So now, finally, after we do all the possible transformations we need, we get this inequality. So we find a range for I. I, the upper bound n, that's easy, upper bound n. Okay? lower bound, floor function of n over 2 plus 1. Floor function n over 2 plus 1. Okay? No problem, right? Here, transformation. Now question, let me ask you. After we do the transformation, now this is what we need, the range for I. Here you have the concrete explicit range for I. Can you tell me how many I's fall into this range? Do the counting. How many I's do you have in this range? Do the counting. Basic counting. How many I's?
And over 2 minus 1.
Draw diagram. Let's draw diagram. All right? The range, upper bound and lower bound. Upper bound n, lower bound n over 2 plus 1 inclusive. Okay? Both numbers counted. All the integers in this range. How do you find the number of integers in the range? Simple counting. All right. Yeah. Let's pause a little bit. Yeah. Remember, I taught you some simple strategy before. Okay? Yeah. Yeah. Later, if you have the similar situation, you can try that. Do some experiments on simple numbers. N equals 3. Upper bound 3, n over 2, floor function 1, 1 plus 1, 2. How many numbers in this range? 2, all right? Where n equals 4. 4 here, floor function 2, that's 3, right? Also 2, okay? Yeah. All right. So then, let me use n equals 7. How about that? N equals 7. 7 here, lower bound, floor function, 7 over 2, 3, 3 plus 1, 4. 4, 5, 6, 4, right? Can you figure out how do you get this number? How do you get this number? Do the counting, simple counting. Here, let me tell you, simple way. This case, which number is 1 earlier than the lower bound? Just 1 before the lower bound. 1. Do subtraction, 3 minus 1, 2. Okay? Which one is just the 1 before 3? 2. 4 minus 2, you get 2. Okay? Here, the number that is just 1 before 4, 3, 7 minus 3, 4. Okay? Yeah. So here, you just find the number right before it. Okay? Right before. Plus 1, right before it. For floor function n over 2, use n minus this. Okay? Here, you do not use the upper bound minus lower bound, because if you minus the lower bound directly, you exclude this one. Okay? Here we want to include. That's why we want to write 1 earlier before that. Okay? That's simple counting. That's the simple counting. Number of elements in the range. Okay? Inclusive. inclusive. All right. So here, our result, answer, n minus floor function of n over 2. Number of leaves, the formula. But for this special case, this is the number of leaves. For this special case, we have another integer expression, the same as this one, but it looks different. Another one. Seeding function of n over 2. Same thing. These two expressions are the same. It can be proved. You just consider even number, odd number. So you plug in even number, correct. Odd number, also correct. Right? All correct. Okay? Yeah. But sometimes we may like to use this one because it looks simpler. One term, right? But sometimes we like to use this one. Yeah. So you have two different formulas you can use. But be careful here. This one it only works for the leaf. Only for the leaf. Because later when we move level higher and higher, the similar equalities won't be true. Yeah. Only this one is true. Later, all inequalities, not equalities. All right, let's move to, yeah. In our textbook, you can find this formula in appendix. In appendix. I'll give you the page number. That's the reason we have this formula. Okay, all right. Next, we just find the number of leaves in a heap. Next, we want to find the number of internal nodes with height 1. So here, the height concept. Here. Let me explain the height concept first. Because, let me tell you, in my previous semesters, when I give questions, I ask students, how many heap nodes with height 1? Now, in a homework question, many students understand the height in the wrong way. Understand height in the wrong way. How did they understand? So here I want to, at this early stage, want to let you know, those students, why it's wrong. So I pointed out. I hope this time you do not make same kind of mistake. Quite a some, actually many. So that's the reason I feel they may not watch the videos. They treat, what's the height? They treat this as height. Height 1, they treat this as height. It's wrong, okay? It's not height. It's not height. They look at it from top, from the root. Actually, we look at height from the bottom. Okay? We look at the height from the bottom, not from top. Okay? All right. Yeah, first, let's look at from the bottom. What is the height for leaves, leaf node? Each node should have a height, right? What's the height for a leaf node? Leaf. Okay? Leaf. Leaf is at the very bottom, right? Very bottom, that means height is 0. For all leaf nodes, height is 0. For leaves. So you look at from the bottom. Okay? Height 1 means, what's height 1? One level higher than the leaf, above the leaf nodes. Height 1 nodes, height 1. One level higher than the leaf. That's height 1 node. Okay? Height 1 nodes. Height 2 nodes. Height 3 nodes. We start from leaves, not from root. Those students, they come from root. Okay? That concept we call the depth. It's not height. depth. Okay? So if you treat, roots as 0, yeah, depth, okay? Depth concept. Yeah, there is a depth concept. But in this class, we do not use depth concept. All right. Now, this time, we want to calculate number of nodes with height 1. These nodes with height 1. Can we use the similar way that we calculate number of leaves to find this formula? Similar way. First, let's look at number of all internal nodes. You know internal nodes, right? For all the heap nodes other than the leaf nodes, the remaining internal nodes. Internal. Leaf we also call the external nodes. Leaf nodes. The same thing as the external nodes. So here, internal nodes. Total nodes and we know the number of leaves, this many. Can you tell me the number of internal nodes? Subtraction, right? Subtraction of these two numbers, the number of internal nodes. Internal nodes. See? Number of these, number of internal nodes. Internal nodes contains the heap nodes of all height greater or equal to 1, right? With all heights greater or equal to 1. Okay? Yeah. All right. Now we want to find the number of internal nodes with height 1. How to find it? We know for the height 1 internal nodes, their children are leaves, right? Children, they are leaves. So if you double that I, those I's, two I's, right? Two I's. The two I's, if I is the height 1 internal, 2I must fall in the range for the leaf nodes. We know that range. We know that range already. Yeah. That's the range. But this time, it's 2I in this range. Not I in this range. 2I in this range. Can we simplify this inequality to get a range for the I here? Division by 2, yeah. But we need the integer operation. Right hand side easy, right? Right hand side easy. But left hand side, how do you get that, right? It's not obvious, right? Here, let me explain it. Let me explain it. Because actually, what we need is this expression. Left-hand side expression, we do division by 2, then take the floor function, but we want to simplify it. How do you know this inequality holds? How do you know it? You need to prove it, okay? We can guess this, but you need to prove it. Here you can do on the scratch paper to prove it. How do you prove it? Look at n mod 4 operation. N mod 4. So n mod 4, you have remainder 0, remainder 1, remainder 2, remainder 3, right? 4 cases. Here, you just verify for all these 4 cases. If it holds, then it holds. Okay? For 4 different remainders. 0, 1, 2, 3. That's the way you prove it. Okay? Here, we do not prove it. We just get a simplified expression. Like that. Now, can you tell me how many I's fall in this range by simple counting. We just learned counting method. This time, can you write that expression out quickly? Quickly. Right? Plus 1 again this time. Answer difference of these two floor functions. Difference of these two. Okay. But this one, less than or equal to n over 2 squared, but not strictly equal. Okay? Sometimes not equal. Sometimes equal, sometimes not equal. So this time we use inequality. For the leaf one, we use equality. Equal. That's the main difference. You should be careful, okay? It's on equal side. You should be careful. But that's for height 1. Height 1. We want to get a formula for all heights. Here I still have 4 minutes. I want to complete that. All height formula. All height formula. The last step. All right. So height 1 formula. Now we want to find height h formula. Height h. Number of internal nodes with any height. Any height. Okay? Yeah, we're almost there. We generalize the previous result. Number of leaves, this one. Yeah. We try to find some rule here. Try to find some rule. That's for height 0. Height 0 formula. Number of nodes in height 0. Okay? Number of nodes with height 1 formula. This is the height 1 formula. I mean the range. This is the range. Then the number of nodes with height 1. That one. So we have 2. Range 1, number of nodes formula. Okay? Can you see some pattern? Can you see some special pattern? Right? Number of nodes with height h this time. Height h. Can you, based on the patterns you have for the first 2 cases, can you do some analogy to get a high h formulas? First, the range is this one. How about that? The range. The range. Yeah. This range. When h equals 0, it's correct, right? For the leaves. When h equals 1, it's also correct for height 1. Right? Then the number of nodes of height h take the difference of these 2 floor functions. Yeah. Straightforward. Okay. All right. So these formulas here, yeah, important because I may give you several questions about the Heapsort. Most of them you need to use formulas on this slide. Okay, on this slide, it can help you solve 4 or 5 questions. Think about that. Okay, if you have 4 or 5 questions, you know, that may impact 16 to 20 points. That many points. Okay? Think about that. That's a lot. Okay? All right, so let's stop here.